8.3 rational functions and their graphs. And we're going to talk about points of discontinuity and asymptotes. So let's get started. All right, so rational function is a function that you can write in the form of a fraction, or f of x equals p of x divided by q of x, and the domain of f of x is going to be all real numbers except those that make the value of the denominator, or q of x, equal 0. So the domain will be everything except for anything that limits it in the denominator. Point of discontinuity is going to be a place in a graph of a function that contains a gap. Now, when we're looking at our calculators and we're graphing these, we are not visibly going to see a circle or a gap in our graph. But if you go to the table of your calculator, you'll see an error at the point of discontinuity. Now, that could happen for two reasons, and we're going to talk about those coming up in just a minute. Anytime you see an error in your table, it is going to be a point of discontinuity. All right, so here are three graphs of rational functions. The first one is y is equal to x squared divided by x plus 1. Now, let me make a comment here. There's no parentheses around these, but you can put your own because this is a group. You cannot split up this because of the plus or the minus in between it. Okay, this is, a quantity that you cannot take and split up and take away these x squares. All right, so don't do it even though there's no parentheses. It's assumed that you know that's a quantity. Now, when you graph this, you're going to get a picture that looks like this. Okay, this one is x plus 3 times x plus 2 divided by x plus 2, and this one has a hole, a point of discontinuity, right here at -2. Okay, and then this one is x plus 4 divided by x minus 2, and then they've got this graph where pieces go here, and they've got this thing going on right here. Okay, so these are points where it breaks up the graph. Are any of these rational functions discontinuous? Well, this one, the way to tell if something is discontinuous as far as just looking at the graph, it's hard to tell unless you have something like this going on or a picture of an actual hole. This one doesn't have either of those, okay, but it could be a discontinuity. But the way you check is if there's some way you can make the denominator equal 0. It doesn't matter what I plug in for x, even if I put a 0 in there, it's still going to make the denominator 1. Okay, so there's nothing I can do to make that 0. So this would be continuous. Oops, let me change the color. Add on yellow. This would be continuous. All right, on this one, if I was to make this x on the bottom and on my rational fraction here, if I was to make this a -2, that would make 0 down here, and that would make a problem and a point of discontinuity. And sure enough, right here is where our hole is, or a gap is, and so yes, this is discontinuous. Over here, if I did the same thing, if I plugged in a 2 right here, that would make it discontinuous. As you can see, it does something weird right here. So this is discontinuous also. It breaks off into two pieces. Easy to see. All right? So let's talk about what causes those things. Some of the reasons why we have points of discontinuity are things called asymptotes. Asymptotes are a line, and I put that in quotation marks because it's not really a line. It would be represented sometimes like in the previous slide where it was dashed, okay, or sometimes in your graph you can actually get a graph, depending on your type of calculator, where it goes like this. Let's see. Nope, let's not draw that. That's just not right. Hang on. You'll have a graph, and say it'll go like this, and then it'll go like this. Okay, something like that. It almost looks like an EKG heartbeat thing. Okay, that would be an asymptote right there, a vertical one on this particular one. All right, it's a line where it causes a restriction in the domain, and the graph will approach it, but it will never intercept, and it will never cross. If it's a vertical asymptote, it will never cross. So this is a picture of y is equal to 1 divided by x. And this is a very important picture because this will talk about the rational functions that we'll be working with. This is like a parent graph to rational functions. All right, and notice how it splits up, okay? And as it's approaching, x is approaching infinity, it will get closer and closer and closer to 0, but it will never cross. Same with as x approaches negative infinity, it will get closer and closer and closer, but will never cross. Same with the y. There is definitely an asymptote this direction too. It will never cross the y at 0, and it will never cross the x at 0. All right. If I plugged in a 0 on the bottom, of course, that would make it undefined, and so therefore that would restrict the domain. So it could be all real numbers, except for x cannot be 0. All right, so as the function approaches x and y axis, it gets closer, but it never intersects. Now, asymptotes, there are 3 different kinds. We are only going to be talking about 2 in Algebra 2. You'll talk about more when you go to pre-cal. But this year, we're only going to be talking about 2. One of them is a horizontal asymptote. In this particular picture right here, there is a horizontal asymptote at 0. And the way you figure that out is by 3 different ways. You will need, I'm going to put this big star, you will need to know how to figure out the horizontal asymptotes. There are 3 different ways. You will need to know these because they will not give this information to you and they expect you to memorize it. Not too much, but it's something you do need to remember. All right, you can have the option of y is equal to 0, and that happens when the degree of the numerator is smaller than the degree of the denominator. Then you can have the choice of no horizontal asymptote at all, and that's when the degree of the numerator is bigger than the denominator. And then you could have y is equal to a number based on the coefficients, and that happens when the degree of the numerator and denominator are the same. Okay, so let's look at some examples of what we've got here with horizontal asymptotes. The first thing you're going to want to look at is the degree of the numerator. And that's based on your variable. So that is a degree of 1. Down on the bottom, we have also a degree of 1. So if the degrees are the same, then you look in the front at the coefficients. Well, the coefficient down here is a 1. So that would be, all the horizontal asymptotes are y equals problems because that's restricting on the range, okay? When we're looking at this, this is horizontal asymptote at 2 over 1, which simplifies to be y is equal to 2. So you abbreviate HA, horizontal asymptote, to be y equal to 2. So in other words, on this particular problem, if it was graphed up here, there would be a horizontal asymptote going across at y is 2, and it will never, it will get closer and closer and closer to that. Horizontal asymptotes can possibly cross, but we won't probably work with too many of those this year. Mostly we'll work with the vertical ones, but you do need to be able to identify the horizontal asymptotes. All right, now, the second example, the degree on the top is a 1, and the degree on the bottom is a 2. So that means the top is smaller than the bottom, so that is automatically a horizontal asymptote at y equals 0. All right, and then the second one, the third one, we have a degree of 2, and then we have a degree of 1. So that means the top is bigger than the bottom. That means automatically that this will not have a horizontal asymptote at all. Okay? So you just look at the degrees and know which one is which. Okay? It just takes a little bit of practice, but you do need to memorize those. All right, let's talk about the other asymptote, and that's a vertical asymptote. All right, vertical asymptotes are whatever will make the denominator equal 0 once you have simplified your rational expression, those things that will make the denominator 0 once it's simplified are vertical asymptotes. And that's where you're going to get this up and down little EKG looking thing if you have a TI-83. Sometimes on the 84s and different ones, they don't actually show this line. Okay? All right, so when you're doing this, you need to look at what you've got. If it's in simplest form, which this one is, then you look at whatever would make the bottom equal to 0. Well, if you set each one of these equal to 0, x minus 2 equals 0, and x minus 3 equals 0, x will be 2, and x will be 3. All right, that is where your vertical asymptotes are. So that restricts your domain, okay? Now, vertical asymptotes, they cannot cross, ever, okay? So when you have this, there will be an error in your table. So your domain will be all real numbers, but x cannot be 2 or 3, okay? And those will show up as errors in your table. These are points of discontinuity, as well as something else we're going to talk about, which are holes. Okay? Holes are points of discontinuity that come when you're simplifying your rational expression, and they're the factors that cross out. Those make the points of discontinuity or holes. So if we were looking at this example right here where we crossed out the x plus 2's, that makes a hole once you set it equal to 0. So if I had x plus 2 equals 0, then x would be negative 2. And that, because it's crossed out, makes a hole at negative 2. Now, then you still could have vertical asymptotes and all that stuff, okay? You need to look and see what you have left over. Remember, if we cross this out, there's really a 1. Make it darker. It's really a 1 on the top, okay? 1 over x minus 3. Now, when you have that, if you set this equal to 0, that would make a vertical asymptote at x is equal to 3, okay? All right, and there's no degree up here, and there's a degree on the bottom, so that would mean that the bottom is bigger than the top, so that would mean a horizontal one, if we wanted to do that one. Oops, I need to do watercolor. A horizontal one at y equals 0, okay? So when you're looking at these, you need to look at all the things that you could possibly have. You could be asked different questions as you're going. So they could ask you for vertical asymptotes. They could ask you for horizontal asymptotes. But this one is going to be horizontal at y is 0 and vertical at x is 3 with a hole at x equals negative 2. So anything that makes the denominator equal 0 restricts or limits that domain. And the domain will not include those values that make holes or vertical asymptotes. Okay? Now, something else that they may ask you to do with these rational expressions is find the x-intercept. So what you're going to want to do is set the numerator equal to 0 once it's simplified. Okay, make a note on here. Once simplified. All right, then you can find the x-intercept. And then the y-intercept, you'll plug in a 0 for x and simplify. So let's go up here and look at the first one. If we set the numerator equal to 0, so the top is the numerator, x plus 1 equals 0, that would give me a x-intercept. Why isn't it writing? X-intercept. If x plus 1 equals 0, then x-intercept would be at negative 1, 0. Oops. All right, and then if I wanted to do the y-intercept, okay, y-intercept, I will plug in a 0 and simplify for everything. So if I plug in a 0 here, I'm going to have a 1 on top. and I plug in a 0 here, I'm going to have a negative 2 times a negative 3, which make a positive 6, so that's 1/6. So my y-intercept would be at 0, 1, 6. Okay, let's do the bottom one here. If I plug in a 0 for everything to get the y-intercept, all right, I'll have 2 over 2 times a negative 3, which is the negative 6, which makes a negative 1/3. So my y-intercept would be 0, negative 1/3. Now, my x-intercept, I set the numerator equal to 0, so my x-intercept would be, in this case, negative 2, 0. Okay, so you could be asked all of these questions based on just the graph. Without even looking at it, you should be able to do all these things. So remember that to find the x-intercept, you set the numerator equal to 0. If you find the y-intercept, you plug in 0 for all the x's and simplify. But the thing with the x-intercept, you must simplify it, cancel stuff out like right here in order to do that, okay? Because if you don't, it's going to, well then this, let me back up the truck on this one. I almost forgot that rule. Okay, that won't be at negative 2, 0. Because if you cancel all that out, it should not have a x-intercept. So let's just double check with the calculator here. Whoops. And we'll type it in and show you. Double check. Whoops, y equals. Okay, so I'm going to type in parentheses x plus 2 and divide that by. I'm going to put extra parentheses because I want to divide by the whole thing on the bottom. X plus 2 and x minus 3. Parentheses, and graph. Okay, so when you're talking about the x-intercept, this is not an intercept right here at at 3. Okay, and if I was to plug in a 0 for the numerator to get my x-intercept, that wouldn't work either because it doesn't actually cross. That never will cross, so you have to simplify it first, so there is no x-intercept here, okay? So make sure you don't mess up and forget to do the simplified version of your graph. And let's look at the table so I can talk to you about it. See how it has an error at 3? That's your vertical asymptote because that's what made it 0 on the bottom. And then at negative 2, that's your error because that is a hole. Okay, so you'll also see that we have your y-intercept at 0, negative 1/3, okay, which is what we found, and there is no x-intercept. Okay, so double check all your work. That should be, why does it keep doing that? I have all these things and it just marks them out. It's negative 1/3. And then there is no x-intercept, okay? So double check your work, but make sure you simplify it before you look for your x-intercept. Otherwise, it will not be true because that's going to give you a hole right there, and it's not going to be crossing right there, okay? All right, so if you have any questions, we'll work on these at school, but come see me if you have any problems. And we'll see you in class.